Hello everyone, welcome to the first lecture of week 6 of the course Power Network Analysis, in which we will continue with our fifth main module, which is transmission line models and the use of these models to understand the steady state performance of these transmission lines under different operating conditions. And in this discussion today, we will specifically understand what this short line model is and how it can be useful for understanding the behavior or performance of the transmission lines under different loading conditions. In the previous lecture, we have talked about at length about the properties of two-port networks, property of symmetricity, reciprocity, what are Z parameters, Y, A, B, C, D, and H parameters, and what relationships hold true for these Z, Y, A, B, C, D, and H parameters for a symmetric reciprocal two-port network. So we will extend this discussion of two-port networks, or essentially we would make use of this discussion of two-port networks to understand what this short line model is and how we can evaluate the corresponding equivalent per phase short line model of a three-phase transmission line. So if you recollect, the models that are typically common in transmission line network literature are three models: short line, medium line, and long line. And as discussed in the previous lecture, short, medium, and long, they don't always refer to the categorization of model in terms of line length. They also depend on what type of operating voltage the line is operating at. So in today's discussion, we would specifically focus on short line model, where our focus would be on line lengths not more than not more than 80 kilometer, and operating voltage of line being less than 69 kilovolt in line to line voltage sense. So also, just a summary of the two-port network. Two-port networks, they usually have this attribute of being linear and lumped, essentially because the two-port network often represents, in power network or transmission line network perspective, they often represent passive networks. So linear and lumped representations are true. Networks often also, in two-port networks, they are symmetric, and in terms of ABCD parameters, it mathematically correlates to value of A and D being same. Networks are also often reciprocal, and for reciprocal condition, in terms of ABCD, AD minus BC should be equal to 1, which we have seen in the previous lecture. And for fixed set of inputs, the network or behavior doesn't change, because the network is essentially a time invariant network with having passive properties of passive representations. So for short line model, often what we have seen even in our transmission line parameter evaluation, that line capacitance per unit length is often small compared to per unit length line resistance and inductance. So for short lines, the line capacitance can be considered to be negligible, and it's often and it's actually ignored for the sake of simplicity in order to have better trade-off in terms of complexity and the associated accuracy of the line model that we are going to understand in terms of the transmission short line model for transmission line. Line parameters are also considered to be lumped. In essence, they are actually distributed, but for short line model, these network parameters can be considered to be lumped. So essentially, two-port networks can be used very efficiently. The reason for all this assumptions or conditions is because for short line models, these aspects do not significantly affect the overall accuracy of the analysis, with results being more or less similar to the actual numbers which we would have obtained, assuming the line parameters to be distributed and capacitance being considered for a short line model. So essentially, if line capacitance is out of window, if it is ignored, short line model is nothing but a series lumped RL circuit on a per phase or a single phase equivalent basis, which looks something like the figure which is shown over here. We have our sending end marked over here with Vs and Is being the per phase sending end voltage and sending end current. Vs and Vr are being measured with respect to a neutral or a ground, so that is where the negative terminal essentially makes sense. Negative terminal actually doesn't make sense in AC network because the polarity in terms of time keeps changing, but we are choosing some reference for measuring these potentials or voltages. So that's where this negative sign or neutral or ground point comes in. So this is basically the ground or the neutral point from which with respect to which Vs and Vr are being measured. The line itself doesn't have any capacitance, or even if it has very negligible capacitance. So what is important is the overall resistance and the corresponding reactance which is coming in because of the line inductance S small l. And on the receiving end, again we have VR/IR, the receiving end voltage, receiving end current, which is essentially feeding in some sort of a load whose apparent power is indicated, or complex power is represented in terms of SR. You would often find small r and capital R being used interchangeably in context of receiving end quantities. So please don't get confused in that regard. So in terms of SR and VR, where SR is the complex power at the receiving end, VR is the receiving end voltage. If we have some load present on the receiving end, then we can evaluate the per phase equivalent receiving end current, which is SR conjugate by VR conjugate. Recollect that complex power is nothing but product of voltage phasor and conjugate of current phasor. So if we rewrite I conjugate as S by V and take conjugate on both the sides. So I conjugate becomes only I, and S becomes S conjugate, V becomes V conjugate. That's how this relationship is defined. And under no load condition, that means there is no load connected to the receiving end, which would mean that the receiving end current itself is 0. So if current is 0, it would mean that the receiving end voltage is not having any complex power at all. So it is also means SR is 0. The voltage, however, need not be 0, because the line is charged and it is getting in some in feed from the source end. So potential need not be 0 for no load condition at the receiving end. Similarly, under short circuit condition, even if the line is charged at the sending end, for short circuit at receiving end, that means that this end is completely shorted from end to end, which means that VR would be 0. And if VR is again 0, in this product context, S would again become 0. So SR is again 0. Remember, IR or receiving end current need not be 0 depending on what sort of energization has come in from the sending end. So under both no load and short circuit conditions, the complex power at the receiving end is going to be 0. The corresponding current and voltages are respectively 0 for no load or short circuit conditions. If we apply KCL at the midpoint of this line, it appears that, at this node A or midpoint, the input current is IS, the output current is IR. There is no other path for any other current to leak out from anywhere, and that's the reason why sending end current is same as receiving end current in short line model. IR and IS, the receiving end current and sending end current, they are the same because line capacitance is neglected, line capacitance is not present. If line capacitance would have been present, unlike R and X, line capacitance would have been represented as a shunt element in a parallel mode circuit, and in that sense, IS would not have been equal to IR because some current would also flow through the shunt capacitances if they were present. Since capacitance effect is neglected in short line model, the sending and receiving end currents are the same. If we apply KVL across this line impedance, which is total impedance Z, then Vs is equal to VR plus Is into Z, where Is is same as IR. And with these equations, overall equations for our short line model, can we not represent them in terms of Z parameters, Y parameters, ABCD parameters, H parameters? Yes. If I were to replace this entire line impedance by a black box and I would call it to be a two-port network where I don't know exactly what is inside this two-port network, then the terminals, they very well similar or represent sending end terminal and receiving end terminal. So if this is the overall equation for a short line model, then I can also represent or re-represent it in terms of a two-port network in terms of Z, Y, ABCD and H parameters. Now that's where something interesting happens. The interesting part is, if I were to use a two-port network in terms of impedance parameters or Z parameters, then there might be certain issues which would come in the next few slides to come. Since ABCD parameters are common parameters to represent transmission line models, so in terms of ABCD parameters, if we correlate or recollect our ABCD parameters, these are the two equations which define the ABCD parameters. If we compare equation by equation, that means equation this with the first equation and the equation sitting over here with this equation, then it's pretty obvious that A is equal to 1, B is equal to Z, C is equal to 0 because there is no term of VR present over here, so C is 0 and D is equal to 1. And the conditions of symmetricity and reciprocity, they eventually are also true because A is equal to D and AD minus BC is equal to 1. So short line model has conditions of symmetricity and reciprocity. It is linear, has lumped representation, and its performance is going to be time invariant because the network properties essentially are all passive elements, so they're not going to change if the inputs are going to remain fixed. If that means, by input I mean, if we change our source frequency from 50 Hz to 60 Hz, definitely the value of X is going to change. So in that condition, a new set of parameters would be defined for this two-port network, and hence time invariancy would come in. As long as inputs remain fixed, R and X, they are not going to change, and that's how the short line model for a given source frequency is going to have a time invariant response. Regarding the aspect that I was talking about in terms of Z parameters, what we see here is that if there is no load at the receiving end, that means IR is 0. That would also mean that IS is 0, and having no load at the receiving end doesn't mean that sending end and receiving end voltages are 0. The source might still be present on the sending end. There need not be a load present at the receiving end. So Vs, as per the equation that we saw here, Vs is equal to Vr plus Is into Z. Is is equal to 0 for no load condition. So Vs is equal to Vr, which need not be equal to 0 depending on the type of source which is present. And if we recollect that when we tried to evaluate Z parameters, which are impedance parameters are ratio of some voltage with respect to some current, and Z12 is specifically the ratio of receiving end voltage by sending end current for no load condition at the receiving end. That means under no load condition for short line, if IR is 0, IS also becomes 0. That means VR by IS is a undefined quantity. If VR by IS is undefined, it would also mean that Z21 will also be undefined. That gives a clue that probably short line model, if we try to represent it as a two-port network in terms of Z parameters, so let's say if I have Z parameters here for this two-port network, then for short line model, this representation is not a valid representation because, as I mentioned, the two-port networks, they are time invariant networks as long as source frequency doesn't change, which is not changing here at all because we are only playing around with the load, whether there is load present or not. Having a load or no load doesn't change the source. So if the source remains the same, Z21 should always be uniquely defined. It is becoming undefined for no load condition. That means there is some problem in the network. So the reason why the problem comes is, in fact, that's where the story or the next aspect comes is that for Z, in fact, Z parameters for short line model, they are absolutely undefined because if we recollect or see our ABCD parameters where C is 0 and try to evaluate Z parameters in terms of ABCD parameters based on the discussion which we had in the previous lecture, then it would appear that Z11, Z12, Z21 and Z22, they would all have inverse of C, where C itself is 0 for short line model. That means none of the Z parameters, not only Z12, but none of the Z parameters are defined for a short line model for two-port network representation. What is wrong in that? Why it is coming up? The answer is very simple. When we try or talk about evaluating impedances in terms of Thevenin's theorem, they essentially mean we are trying to do some open circuit short circuit arrangement. It's mostly open circuit arrangement where we are trying to find a ratio of a voltage with respect to a current. So essentially we are trying to find the effective Thevenin impedance from sending end perspective or receiving end perspective while opening out either ends. If the impedances themselves are undefined, That means Thevenin impedance is also undefined. It cannot be evaluated for a short line at no load condition. Why is that happening? So the Thevenin impedance is not invalid. If in fact these ratios, they are all equal to Thevenin impedance or effective Thevenin impedance. What we see here is that why these impedances are not defined. In case the short line model doesn't have any load, it means that essentially this representation of Z hasn't got any role. It is as if this entire Z, even if it is to be removed or cut off, we would still have an analogous condition where we have Vs on one end, Vr on other end, and here is my ground or terminal where the reference is being measured. Whether there is impedance in between Vs and Vr, or whether there is no impedance between Vs and Vr, under no load condition, the current in the circuit is always zero. If the current itself is always zero, what is the need of having a short line model at all? That's what I mentioned, that if I cut off this entire section and only connect these two terminals, Vs and Vr, the way it is shown over here, by a short circuit path, the short line model necessity is at all gone. There is no need of having a short line model. And that is probably the reason why short line model cannot be represented in terms of impedance parameters, because impedance parameters are not important or not valuable for short line model under no load condition. And that's the reason why the Z parameters for short line model cannot be defined or cannot be evaluated. The other parameters, however, that means Y and H parameters, they can very well be obtained, because in terms of Y parameters, admittances, where we often do short circuit studies to find the corresponding admittances, because these are ratios of current with respect to voltages. For short circuit of the receiving end, the currents need not be zero. The receiving end voltage, however, would be zero, and Vs would be equal to Is into Z. Effective line admittance, it is often evaluated under short circuit conditions. So Y parameters, they are very well defined in terms of ABCD, and conditions of symmetricity and reciprocity are true even for Y parameter based two-port network. Same analysis or same logic is also true for H parameters for a short line model. The terms can be well defined, and conditions of symmetricity and reciprocity are also applicable as per the mathematical properties. H parameters, they are basically combinations of partial ABCD parameters and admittance parameters. Why do I call that? Because in H parameters, essentially we represent Vs and IR in terms of the remaining voltages and current on the other side, and that's where it's a combination of ABCD and admittance parameters. The first equation relating to ABCD equation, whereas the second IR current represented to the admittance parameter equation. Coming to the performance of short line model under different conditions, usually the sending end voltages, they remain frozen. So for fixed Vs, the receiving end voltage would change depending on what is the load connected to the receiving end. Under no load condition, the currents are zero, so Vs is same as Vr. We have seen that in the previous few slides also. At full load conditions or partial load conditions, the receiving end current need not be zero, and usually the sending end voltage magnitude would be more than the receiving end voltage magnitude, essentially indicating that the aspect of Ferranti effect, which we will talk about in length when we discuss further in the next few lectures, that is likely not going to happen often, because line capacitance itself is not considered in a short line model. And since the voltages are changing as per the loading condition, we can also define the percentage voltage regulation similar to percentage voltage regulation defined for conventional transformers and generators. The percentage voltage regulation is nothing but a measure of line voltage drop from no load condition to full load condition. And this percentage voltage regulation would very significantly depend on what type of load is connected, specifically what type of power factor the load is connected, whether it is a leading load or a lagging load. That would dictate the percentage voltage regulation to be positive or negative as well. The slide here shows the typical phasor diagram for short line model. Remember, the phasor diagrams, they are all coming in from the aspect that Vs is equal to Vr plus Is into Z, and IR is equal to Is. Here we have chosen Vr, which is the receiving end voltage, as the reference for all phasor quantities in this particular equation. IS is also being measured with respect to receiving end voltage. So depending on the load which is present, so basically Vs is leading, I mean I just assumed some angle delta. Delta need not be leading always, it could also be different for different loading conditions, and corresponding phase angle theta of the receiving end current, because this is also equal to IS phasor, this can also change. For lagging power factor, that means the receiving end current is lagging the receiving end voltage by an angle theta. So theta is essentially marked as this purple color line, which is the one which you see over here. IR is lagging the receiving end voltage. The corresponding sending end voltage magnitude is typically more than the receiving end voltage magnitude. That's what the comparison of this property means. So this is VR. I think I have marked other quantities over here. So this, the red line is VR. The blue line is voltage drop across resistance. The purple line is voltage drop across the line reactance. So in terms of magnitude, VR is typically less than the sending end voltage magnitude. So usually it will remain generally positive for lagging power factor load. But for leading power factor load, which is the case shown over here, where current is leading the corresponding receiving end voltage, it might happen that the no load condition voltage can become more than the full load voltage condition, and hence the positive voltage regulation can become negative in certain cases. So on similar lines, we can also define the apparent power or complex power at the sending end, which is, if we know what is Vs and Is, then we can find Ss as product of Vs into conjugate of Is. The example that is discussed over here would essentially replicate the fact that how voltage regulation can be positive or negative. Usually for lagging power factor loads, the VR is positive as we have seen, but for like leading power factor loads, VR can become negative also. And remember, recollect, VR is nothing but the measure of line voltage drop from no load condition to full load condition, with sending end voltage remaining fixed. So there is no notion of Ferranti effect in this particular context. So what we have here is a transmission line whose operating voltage is 69 kV. Remember, it is less than 69 kV. And line length is 40 kilometers, which is again less than 80 kilometers. So if we have to model this line, we can very well use the short line model. And that is the reason why only the line resistance in per kilometer and line inductance on per kilometer basis are defined. Shunt capacitance is negligible. We have to find the voltage power at the sending end and voltage regulation when the receiving end of the line is having this voltage or this load at 66 kV under different power factors, lagging and leading. The other numbers, if you compare, they are precisely the same. The power factor quantum is same. The apparent power specification of the receiving end load is also same. Only the power factor is changing from lagging to leading. So what we would do, we find the corresponding net Z of the entire line length of 40 kilometers, which is close to 6 plus J20 ohms. We assume receiving end voltage to be our reference for all phasors, since it is line to line voltage. So we divide it by root 3. The phasor is 0, acting as reference. Divided by root 3 gives us the corresponding phase voltage. So it is 38.105 and an angle 0 kilovolt. Power factor is 0.8 lagging, and the receiving end voltage is fixed at 66 kV. So we can definitely find the quantum of or the phasor of the corresponding receiving end current. Power factor lagging means the corresponding power factor angle is 36.87 degrees. And since current is lagging the receiving end voltage, so we have a negative sign here. And also the quantum of three-phase power or apparent power is given, so we can divide it by 3, get the corresponding per phase apparent power magnitude, apparent power value. And when we divide this apparent power by the per phase voltage, we can get the corresponding per phase current. So essentially IR is 1000 at an angle minus 36.87 degrees ampere. We know what is VR, we know what is IR, we know what is Z, which is given over here. So essentially we can find the value of Vs also. And we can also find the corresponding sending end per phase complex power in terms of Vs and IR conjugate. So basically Vs per phase voltage magnitude is 56.288 kV. So if we find the line to line voltage, we multiply it by root 3. We find the total 3-phase apparent power, multiply it by 3. and percentage voltage regulation is positive 47.72%. Now the same quantum of load, now it is leading, the second case. So leading means the angle of current is leading the receiving end voltage. So 36.87 degrees comes in instead of minus 36.87 degrees. Remaining quantities or magnitudes, they remain more or less same. So receiving end per phase apparent power is quantum is same. The magnitude of current also remains the same. What changes drastically is the magnitude of the sending end voltage as well as the magnitude of the complex power or the apparent power, with phase angle being drastically different. So in terms of the line to line voltage and three phase power, the quantums are different. So here we have 109.788 MVA as the sending end power, whereas in the other case we had 168.864 MVA. Now, the reason probably why this total apparent power has been reduced from lagging load to leading load is because with leading load, reactive power can still be generated and the line need not consume that power from sending end. And probably that's the reason why 168.864 MVA is going down to 109.788 MVA, because excess reactive power at the load end, which is the leading power factor load, is being utilized by the line to charge itself. So we'll also talk about charging current when we discuss few more next few discussions. And in this particular condition with leading power factor load, the overall voltage regulation is a negative quantity. So with that, I conclude this discussion, and in the next lecture, we will start with the notion of medium line model, again building upon how two-port networks can be used to model medium line model, and we'll see how medium line differs from short line model. Thank you.